we have this power series, and if we write down a few terms, it looks like when n is 1, this is x minus 2 to the first power over 1. X minus 2 to the second power over 2. X minus 2 to the third power over 3. Plus that. Now we get such power series by taking taking Taylor series of some given functions. And you immediately see that for some values of x, this series doesn't make sense. So for example, if I have x equals to 3, what's 3 minus 2?
1.
1. So it would be 1 over 1, 1 over 2, 1 squared is 1. So 1 over 2, 1 over 3. Does that series converge or diverge?
That series converges.
No, it diverges.
Diverges. Why?
Diverges because it's over n. It's basically, you could do 1 over n, and that diverges.
Okay.
So therefore, I
You have
kind of just substitute.
Okay. You need.
That's how.
Right.
That's how
If
I
you
thought
plug in
about it.
3, it's 1 over n, and I wasn't asking for that. I was asking why does this diverge? Do you need
Because it's a
harmonic, right? It's a harmonic series, or it's a p series with p equals to 1, right? So it diverges. So when you plug in 3 into x, we know it diverges. And immediately you'll see that if you plug in anything higher than 3, you will diverge much faster. Because if you say plug in 4, that's like 2 squared. That's much bigger than 1 over n, right? If you have 2 to the nth power on the top, that's much bigger than just having 1 over n, right? So this all says that the following series may have serious problem with convergence for certain values of x, right? So here's the question that would naturally arise once you start plugging in values. For what values of x does this converge? And to answer this problem, you have to use some kind of tests, right? And for most cases, we'll just always use the ratio test. Okay? So, tip: use ratio test. Some cases it's easier to use the root test. You know how to use root test. You take the nth root. Right? If you take the nth root, this n will cancel away, but down here you will have the nth root of n. And do you remember what this limit is when n goes to infinity? 1, right. So we did this last time. So if you remember this, actually for this question, it's easier to do the root test rather than the ratio test. But because most cases it's ratio test that's easier, we'll just use ratio test for everything. Okay? To use ratio test, first write down what the term is that you're adding.
So an equals to x minus 2
Over n.
And then
an plus 1 would be
x minus 1, minus 2 raised to the n plus 1 power over n plus 1.
And then you have to calculate the r, which is the limit of n going to infinity of an plus 1 over an absolute value. Now, in some of the earlier examples of ratio test, I just didn't write this absolute value at all because the terms that we were adding were already positive, right? But here, you have to be careful. If x is less than 2, then you have negative number to the nth power, and sometimes that alternates. So when you have negative numbers, it's important that you keep this absolute value, right? So we'll keep the absolute value. Plug these in. Let's see, limit n going to infinity of x minus 2 to the n plus 1 over n plus 1 over x minus 2 to the nth power over n, absolute value. And you're dividing fraction by a fraction, so what do? Keep, change, flip. Keep the top unchanged. But then you change the division to multiplication. You flip the fraction in the denominator, so it'd be n over x minus 2 to the nth power. You still need the absolute value. And it's easier to divide this by this because some of these cancel, right? So you have x minus 2 to the n plus 1 over x minus 2 to the nth power. And also pair the n with n plus 1, absolute value. And now since these two have the same base, what's the rule for exponents? If you have the same base, what do? You divide, you have to subtract. So dividing two exponents, two exponential forms with the same base, you subtract the exponents. So you have limit n going to infinity of n plus 1 minus n would cancel the n's, and you just have 1. So we'll just give you x minus 2. And then this will be, we can just take the absolute value separately. Now let's think about this one. See, x minus 2 now has nothing to do with the n. So the only thing that you have to worry about when you send n to infinity is this one. What's this limit as n goes to infinity?
1 over n plus 1?
It's undefined.
Oh, just 1.
It's just
Yeah.
1, right. As n goes to infinity, it's n and n, right?
Yeah, I was thinking about the 1 also. I was like,
No. Yeah. So it's, when n goes to infinity, this is 1. Or you can just use the L'Hopital's. This is infinity over infinity, so if you differentiate top and the bottom, it's 1 over 1. So that gives you just absolute value of x minus 2. Okay. Now let's recall what the ratio test says. If r is less than 1, what do we know? Converges. When r is 1, what do we know?
Inconclusive.
Inconclusive. And when r is bigger than 1, diverges. So because of this, here's what we know. If this is less than 1, then the original series converges. If this is equal to 1, then we don't know. We'll have to do other tests, okay? But if it's bigger than 1, then it definitely diverges, right? So if absolute value of x minus 1 is less than 1, we know that the series converges. Minus 2. Okay, and now let me give you some idea of how to solve an absolute value inequality like this. So first of all, if x minus 2 absolute value is less than 1, definitely the x minus 2 itself should be less than 1, because if it doesn't, then you're in trouble, right? If x minus 2 is, say, 3, then absolute value of 3 is bigger than 1, so this doesn't work, right? However, this can't be too big of a negative number either, because if this is like negative 10, what happens if x minus 2 is negative 10 and you take absolute value? You get positive 10, so it doesn't satisfy this, right?
Okay.
So this has to be at least what? Negative 1, right? So that's how you solve an absolute value inequality. If you have absolute value less than some number, you just put the positive and the negative, and this number falls in below. Okay? And after this, you can add to both sides, actually to all three sides, and that gives you x has to be less than 3, and x has to be less than 1, because negative 1 plus 2 is 1.
You add plus, you do plus 2 because it's x minus 2.
Yeah, so that this negative 2 will cancel, and now you see that x has to be a value between 1 and 3 for us to know it definitely converges. However, this boundary value is 1 and 3. That's going to cause a problem. See, if x is 1 or x is 3, then absolute value of that will give you 1, right? If x is 1, 1 minus 2 will be negative 1, absolute value gives you 1. So when x is 1, and then when x is 3, these are cases when this becomes 1, and therefore the ratio test says, no, it's not going to work. You need to use other tests. So we have to use other tests for these two cases. Yes?
So with the unequal signs, so because it says x has to be greater than and less than instead of less than and equal to.
Right?
So if the inequality says that x isn't 1, right?
So this is the case when it falls to r less than 1. These are the cases when it falls to inconclusive. So for those cases, we don't know yet. We just know, all we know is that if x falls in here and there, it definitely converges. Or if x is bigger than 3 or strictly less than 1, then it diverges.
Okay.
But for these two cases, x equals to 1 and x equals to 3, we don't know whether it's going to converge or not. And that has to be dealt separately.
Okay.
All right, so for x equals to 1, you have summation n equals to 1 through infinity 1 minus 2 to the nth power over n, which is summation n equals to 1 through infinity of negative 1 to the nth power over n. Now, does this converge or not? What do you think?
No.
It's
No?
also 1.
Why do you
Yes,
say
it
no?
does. It does converge because it's negative, so it just like is the opposite of 1 over n.
Series.
Well,
No.
You could take the alternating thing out and then
Okay.
do
Sorry. The thing is, this cannot be taken outside the summation because this has n there.
Like, can you do the absolute value?
Okay, so first of all, the absolute value of this wouldn't converge, right?
Right.
So when you have something that's alternating, the first thing that you might want to do is take the absolute value, see if that converges. Then the original series converges absolutely, right? However, if it's alternating and the absolute value doesn't converge, sometimes the alternating version might still converge, right? In that case, we say the series converges conditionally. Okay? So for alternating series, there are two types of convergence. It's only important if you're writing Python programs and for some reason you want to switch the order of addition, because if something's conditionally convergent, you shouldn't switch orders of addition because it might give you a totally wrong answer, okay? So, but anyways, what I'm trying to say is that this one definitely does not converge absolutely, because if you take the absolute value, it's 1 over n, it's a harmonic series, and you know well that that doesn't converge. Yes?
Can you prove that with the root? The root group?
I've explained that you can use the root test for this case as well, and it will be actually slightly easier, but the end result will be the same. This will be your R, and you'll still end up with the same boundary that you don't know what to do. Okay? You know, because root test is known to be stronger than ratio, you might think, oh, that could be beneficial in some cases, but in these types of cases, it doesn't really give us anything new. Okay. All right. What am I trying to do? Oh, yeah. So we have this alternating series. How do you prove convergence of an alternating series?
Plug in a number. You don't just do the absolute.
No, there's something called alternating series test.
The limit says limit absolute.
Right, right. Alternating series test has two parts. You have to check for two things. First, set the limit of n going to infinity of the absolute value. And this is limit of n going to infinity of 1 over n, which is 0, right? So that's the first requirement. If you have an alternating series, that a series where plus and minus switch, plus and then the next one is negative and the next one is plus, you want to check two things. One is that the sequence themselves has to go to 0. Do you remember the second condition?
A and plus at the absolute value has to be less than or equal to the absolute value of a.
See, absolute value of a n plus 1 has to be less than the next one. In other words, these series must be decreasing. The sequence must be decreasing. Okay? So you have absolute value with n plus 1. And absolute values don't care about negative 1 to any power, so this is the same thing as just 1 over n plus 1. Now, this would be less than 1 over n. Why? Why is this less than 1 over n?
It's going faster in the model because the plus one.
The denominator is smaller here, right?
Mm-hmm.
Bigger the denominator, the smaller the fraction. So that's true, but that's absolute value of a n. Yes?
So after the 1 over n plus 1, would you not put it to the n plus 1 power? After you nix the absolute value bars? Then
Yeah, the sole purpose of this is so that it changes plus and minus for different values of n, right?
Right.
But if you take the absolute value, that doesn't do anything, right? What does this evaluate to? It evaluates to negative 1 if n plus 1 is odd.
Okay.
If n plus 1 is even, then it evaluates to positive 1, right?
Oh, so it's just 1 no matter. Okay.
Yeah, it's always 1 whether if you take the absolute value.
Okay.
So that's why I just put 1.
Okay.
All right, so because these two conditions are met, this one and this one, that says this case converges by alternating series test. Okay, on the other hand, let's try to plug in 3 into this series. So if I replace x by 3, what is that? That's 3 minus 2 to the nth power over n from 1 to infinity. And this one is something that everyone knows. Does this converge or diverge?
Diverge.
Diverges because it's a harmonic series. Okay. Yeah. Yes?
Do you say that this converges conditionally?
Oh, that's a very good question. Yeah. So I just said converges by AST because when we're trying to answer interval convergence or radius convergence, we don't really care if it converges conditionally or not. So I just wrote converges by AST, but it would be even better if you write down converges conditionally by AST. Okay. All right, so now let's write down the answer. The answer is therefore the interval of convergence is, it includes 1, and it's up to 3, right? But it excludes 3. This is the same thing as saying x has to be between 1 to 3 while including 1, right? So that's the integral of convergence. The radius of convergence is it's the half of the length of the interval. So if you have like 1 to 3, then half the length of this length is 3 minus 1, which is 2. But that's the diameter of the interval, that's what they call it, and the radius is half the diameter, so this length will be 1. Right? So radius of convergence will be 3 minus 1, you divide by 2 because you're getting the radius, it's equal to 1. Now, later on you'll see that actually this number 1 is this number right here. If you have x minus some number, absolute value less than some number, this number on the right side is the radius of convergence. Okay. So you can take a shortcut there. Oh, yes, you have a question.
How come we see for the other one it's harmonic, that one is not harmonic too?
This one, let's write this down. What is this?
Because you said it's always going to be negative or a positive 1.
So when n is 1, what is it? Negative 1 over 1, right?
Yeah.
When n is 2, what happens?
It becomes 1 over 2.
1 over 2 plus 1 over 2, right? And then minus
1 over 3.
1 over 3 plus 1 over 4 minus 1/5, right? Now, what this does is like you start from 0 and you jump negative 1 to the left, and you go 1/2 to the positive, and you come back by 1/3, go back and forth. And there are two things that are guaranteed by the alternating series tests. First is that the jumps are getting smaller and smaller. As you go back and forth, the jumps are getting, so you start from some big jump and then get smaller and smaller. And eventually the jumps become 0 at infinity. And if those two conditions are met, you can kind of see why that means that the series must converge. Right? You're adding all these jumps, and it has to eventually get closer and closer to some value. That's the big difference between this case and then the other case.
Isn't this also the one that you said you could like force it to like go to a certain number if you wanted to?
Yeah, this is called conditionally convergent series, and Riemann saw that if you have something that's not absolutely convergent and only conditionally convergent, you can switch the order of addition and somehow make it to converge to anything you want. So that's why saying conditionally convergent may be important. Like let's say you did this math analysis and handed it over to somebody who doesn't know math but can only program, right? And the other person decides, well, it's easier to add only the positive parts first and then negative parts first and next. Yeah. Then you have to tell them, no, don't do that because it's going to be a bad approximation. You have to do that. Yeah. Any other questions?